Hello Year 12 further mathematicians. I'm just going to move on from the internal exams now and start a chapter in the Core Pure 1 further maths book. Chapter 1 to do with complex numbers, and 1.1, the first subsection, is to do with imaginary and complex numbers. Now, just going to talk about the origins of imaginary and complex numbers, where they came from, how they were discovered, why they are used. So it came from the idea of every equation effectively having a solution. So as you may know, there are some equations, some quadratic equations, for example, which only have one solution or two solutions. But there are then some which have no solutions. For example, if you considered the basic quadratic x squared plus 9 is equal to 0, and I said to you, solve this equation, you would potentially attempt to subtract 9, then you would square root, and then you would say this is a math error. So no solutions. Now, mathematicians for hundreds of years were pretty happy with this area of maths, that the concept of square rooting a negative number doesn't make sense. So we would have math errors and we'd have some equations with no solution. But then about probably 300-400 years ago, they then decided that wasn't good enough. We needed to invent effectively a new number which would allow us to find solutions to any equation. And in fact, all quadratics then would have two answers, not counting repetition. And then all cubics as well would have three answers. Quartics would have four answers. Quintics would have five answers, instead of having some gaps in there. And this era of maths became known as the fundamental theorem of algebra, which is a really fancy way of saying every equation effectively, what the highest power is, it will have that many solutions. So the number they invented was called I, and I represents the square root of -1. Previously that wasn't a thing, but now that is a thing. And then it came to a new set of numbers called imaginary numbers. So imaginary numbers would be multiples of I, where that multiple is a real number. So that could be 3i, 4i, minus 5i, 3.8i, root 6i, etc. Any real number I represents an imaginary number. And then the concept of something called a complex number, which is a real number plus an imaginary number. So A plus BI. So the A and the B, the coefficients, represent real numbers. So that could be something like 6 plus 5i, 3 minus 2i, root 5 minus root 3i, and so on. Okay, so you've got something now called a complex number. Okay, and visually, the complex numbers, if I represent the complex numbers as a set with that circle, the letter they use for complex numbers is a bold C. Inside that set, there would be the real numbers. They're a subset. Okay, inside that little subset would be every number on a number line. So from 0, 1, 2, 3, all the whole numbers, all the fractions, all the decimals, all the surds, pi, e, everything would be inside that circle. Because the cheat is, if I wanted to write that as a complex number, it would be, saying that the number 3 is a complex number, it would be 3 plus 0i. So that's why the real numbers are a subset. And there would be another circle then, which would be the imaginary numbers. Now there's no symbol to represent the imaginary numbers, so it's just going to call it imaginary. And that would be numbers like 3i, I itself, root 7i, so on. Okay, and again, that's a subset because you could write every single imaginary number as 0 plus something I, so that's why it's a complex number. And complex numbers is the big set, then you've got the real numbers and the imaginary numbers. Now, if you want me to actually place some numbers in there, for example, a number 3.5 would be a real number, that'd be in there. The number 7i would be in there, and then stuff which is not in those circles but still in complex numbers would be something like 2 plus root 2i. That would be on the outside. Okay, and the letters that they tend to use for complex numbers now is the letter Z. So the letter Z is used to represent complex numbers. Now this is pretty handy because in all of single maths you never ever consider complex numbers. Okay, all of the equations you do in single maths, most of them have an x. But when mathematicians want to consider complex numbers, rather than using the letter x, they use the letter z. And then you know, right, for these questions, complex numbers are a thing, I am going to use those instead. Okay, let's see what a few examples, basic examples would now look like. So we're going to write the answer to these square roots now, and rather than just type math error, we're going to write them using imaginary numbers in terms of I. So you might remember doing surds previously, but normally when you do a surds question, if this was a positive number, you would rewrite it as times in by the biggest square number. And you use a very similar concept with this. So I'm going to write this as root 36 times root minus 1. And then simplify root 36 to 6 and simplify root negative 1 to I. So 6i would be the answer to that square root. No longer math error, no longer can't square root negatives. Now we can. We just needed to invent a new number. Root negative 28 would be, okay, let's do this in 2 steps. It'd be root 28 times root negative 1. But then you should know that root 28 is root 4 times root 7 times root negative 1, which is the same as 2 root 7i. So the coefficient of that is 2 root 7. Now, makes sense. That's intuitively what you would do. Now we're going to do some simplifying. So we've got a few complex numbers now. And the good news with this is it's effectively the same as collecting like terms. So the letter I is just considered as a like term, effectively. So you can expand the brackets, collect like terms, and it works perfectly. So expanding brackets works. Write that as 2 separate fractions. You'd have 10 over 2 and 6i over 2, and it would work as you would expect. Collect the like terms. So the real part is 10 plus 5. The imaginary part is negative 16i plus 3i, which is negative 13i. and that is a complex number. There's no way to simplify that. It is 15 minus 13i. Okay. Part B, I want to simplify a slightly more complicated looking version. 6 minus 3i over root 3. One way to do this is to write as two separate fractions. And even though that looks like a complex number, these coefficients, the real part and the imaginary part, are not simplified surds. Okay, so if I focused on just that part there, 6 over root 3, simplify that, surd. And 3 over root 3, simplify that, surd. Root 3 times root 3 is 3, and you can divide by 3 to get 2 root 3 minus root 3 times root 3 is 3, 3 divided by 3 is 1, so that's minus root 3i. And that would be that as a simplified complex number. So yeah, the main concept is we've now invented a new number, root negative 1, which allows us to solve any equation. So quadratics we're going to kind of start off with, but any cubic, quartic, quintic, any polynomial now definitely has roots or solutions because we've invented this new number. Now the questions I would like you to complete are on page 7. And you are going to try question 1, question 3, and you're going to do the odd parts. And then you're going to do question 4, question 6, and question 7. And that'll be it.